Greetings, everybody. Learning is a hobby here. I want to go over chapter 29 in Spivak's calculus book, which is the chapter where he constructs the real numbers using Dedekind cuts. So that's what we're going to do here. Let me bring up my lecture notes and we'll go through the construction. Right. And just so you know, this is kind of a long chapter, which means most likely a longish type of video, but that's just the nature of this construction. We got to get through it, so let's do it. So we'll start with the definition of a Dedekind cut. Um, a real number is a set alpha of rational numbers with the following four properties. So here are the four properties of a cut. If x is an element of alpha and y is a rational number with y less than x, then y is also in alpha. Then property 2, alpha is not empty. Property 3, alpha is not the entire set of rational numbers. Property 4, there's no greatest element in alpha. In other words, if x is in alpha, then there's some y in alpha with y greater than x. And then Spivak just reminds us that we use the symbol r for the real numbers. All right, so this is what we're going to use for our definition of the real numbers, and we'll go through the construction here, showing that this set with with these definitions and the way that we define the operations, we get a complete ordered field. Okay, so there's a few notes here. If we temporarily regard the real numbers as known, then it's not hard to check that a set A with these properties is indeed a set of rational numbers less than some real number alpha. We've actually done this as an exercise. So if you go back to my video on chapter 8, if you the solutions to exercise set for chapter 8, if you look at problem 817, we actually did this one on the channel way back when we did chapter 8. So if you want to see that, you can go back to that video. Um, okay, here's an example of a real number defined as a Dedekind cut. So square root of 2 is equal to the set of all rational numbers x, where x is less than 0, or x squared is less than 2. And Tao says it's not an entirely trivial exercise to show that square root of 2 is a real number. We would need to prove this using only facts about the rationals. The hard part would be checking property 4, but as it happens, we've already done this in a previous chapter, so we won't do it again here. Okay, another note. Condition 4 is necessary to avoid ambiguity. For example, the set of all rationals such that x is less than 1 and the set of all rationals such that x is less than or equal to 1 would be candidates for the real number 1. Right? So to to uh, eliminate that vagary, that vagueness, we need property number 4. A rational number is not a collection of rational numbers, but we can identify the rational number q with the real number of the set of all rationals with x less than q. Later, we will ignore this distinction. Okay, there's a lot of notes here. Henceforth, rational numbers will be denoted by lowercase Roman letters, X, Y, Z, A, B, C, etc., and real numbers by lowercase Greek letters, alpha, beta, gamma, and capital Roman letters, as usual, would denote sets of real numbers. So, capital A, capital B, capital C, etc. This is sort of like standard notation for this type of construction. All right, so now we get to our second definition. If alpha and beta are real numbers, then alpha less than beta means that alpha is contained in beta. That is, every element of alpha is also an element of beta, but alpha is not equal to beta. And another note here, Spivak does not explicitly define greater than or equal, but they're similarly defined as in the above definition. For example, alpha beta real numbers, then alpha less than equal beta, if and only if alpha is contained in beta. Okay, first theorem. If A is a set of real numbers and A is not empty and A is bounded above, then A has a least upper bound. Right? So that's one of the important properties of the real numbers, if you remember. All right, so here's our candidate for the upper bound. For the least upper bound, sorry, let beta equal the union of all of the alphas in the set A. All right, there's two parts to this proof. First, we have to prove that beta is a real number, and then we show that it's the least upper bound for all the set of all the alphas. So this for the set A. Okay, so to show that beta is a real number, there's the four properties that we have to show. So let x be an element of beta, then x is an alpha for some alpha in A, since alpha is a real number and y is a rational number where y is less than x, that implies y is an x. Therefore, y is an element of beta. Okay, sorry about that. I had to pause for a second. Hopefully that didn't that didn't upset the video too much. Let's continue here. Um, okay, property number two, A not empty implies that the union of the alphas is not empty. Property three, since A is bounded above, there's some Q in the rationals such that alpha less than or equal to Q for all alpha in A. Therefore, alpha less than Q alpha less than or equal to Q less than Q plus one implies Q plus one is an element of the rationals, right? Because Q is closed under addition, and Q plus one is not in beta, therefore beta is not all of Q. And then finally, property four, assume beta has a greatest element y, then y is an element of alpha for some alpha in A. Since y is greater than or equal to alpha for all alpha in A, y is the greatest element of one of the alphas, which contradicts that alpha is a real number. Therefore, beta has no greatest element. So properties one through four are satisfied, which means beta is a real number. Okay, then we also, now that we know that beta is a real number, we also have to show that it's the supremum of the set A, or in other words, it's the least upper bound. Okay, so since beta is the union of all the alphas in A, alpha is a subset of beta for all alpha in A, which implies that alpha is less than or equal to beta for all alpha in A. So that means that beta is an upper bound for A. Then if we let gamma less than beta be another upper bound for A, but gamma not equal to beta, then there is some x in beta such that x is not an element of gamma. However, x in beta implies x is in alpha for some alpha in A. So that means that gamma is a subset of alpha, which contradicts that gamma is an upper bound for the set A. Therefore, beta is the least upper bound for A. Okay. Then we get to another definition. If alpha and beta are real numbers, then alpha plus beta is defined to be the set of all x, such that x is y plus z for some y in alpha and some z in beta. And then we get a theorem after that. If alpha and beta are real numbers, then alpha plus beta is a real number. And again, we have to show that the four properties are satisfied. Um, which we do here in the proof. Let x be an element of alpha plus beta, and let y be a rational number such that y is less than x. Then x is p plus q for some p in alpha, q in beta. Then x minus p is equal to q, and we know that q is an element of beta. And y less than x implies y is p plus y minus p, which is less than p plus x minus p, which is equal to x, and p is an element of alpha, y minus p is an element of beta, since beta is a real number, and that implies that y is an element of alpha plus beta. So that's property one. Property two, alpha is not empty and beta is not empty, which implies that there is a p in alpha, a q in beta, such that p plus q is an element of alpha plus beta, so alpha plus beta is not empty. Property number three, alpha and beta real numbers implies alpha is not the entire set of rationals, and beta is not the entire set of rationals, which implies that there are rationals p and q in the rationals, such that p is not an element of alpha, q is not an element of beta. Then for right, because real numbers are bounded above. Then for any x in alpha, x less than p, since if p is less than x, that implies that p is an alpha. Similarly, for any y in beta, y is less than q, which implies that for any x in alpha, y in beta, x plus y is less than p plus q, which implies that p plus q is not in alpha plus beta, which means that alpha plus beta is not all of the rational numbers. Right, and then finally, property number four, let x be an element of alpha plus beta, then x is p plus q for some p in alpha, q in beta. Since alpha, beta are real numbers, there are rationals Rs such that p is less than r, and R is in alpha, Q is less than S, and S is in beta, then R plus S is an element of the rationals, and R plus S is an element of alpha plus beta. Furthermore, X is less than R plus S, therefore alpha plus beta has no greatest element. So that shows that the sum of two real numbers is a real number. All right, another theorem. Um, Next, we show that that addition is associative. So if alpha and beta and gamma are real numbers, then if we add alpha and beta first and then add that to gamma, that's the same real number as adding beta and gamma and then adding alpha to it. Right, so here's the proof. For any rationals P, Q, R with P and alpha, Q and beta, R and gamma, P plus Q uh, in parentheses plus R is an element of alpha plus beta in parentheses plus gamma. However, P plus Q plus R equals P plus, and then in parentheses Q plus R by associativity of addition in Q. So that means that those two numbers are equal to each other. And since the right-hand side of that equality is in the set alpha plus beta plus alpha plus in parentheses beta plus gamma, that means that the left-hand side um, actually it goes both ways. So that shows that the left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. So you get associativity. Okay, we have another theorem. If alpha beta are real numbers, then alpha plus beta is beta plus alpha. So commutative law holds. And I didn't feel like writing out another one of these. It's very similar to the one that we did for associativity. So I just said this follows from commutativity of addition of rationals. Um, it's very similar to the one for associativity. So now we have a definition. We define the real number zero to be the set of all rationals where x is less than the rational number zero, right? And we have to show here I'm showing that zero is a real number. I won't belabor this. A lot of these proofs are very tedious. So if something like this, where we've done this type of proof already a bunch of times, even in this short we haven't even gotten very far into chapter 29 yet, but I'll just say you show that the four properties hold, and that's what I did here. If you want to pause your screen and look at this in detail, you can, or you can go to the Patreon page and download the PDF for for this section. All right. So next we have a theorem. If alpha is a real number, then alpha plus zero is alpha. Here's my proof. Let let x in alpha. Then there's some y in the rationals such that x less than y and y is in alpha. Then x minus y is less than x minus y over 2, which is less than 0. Here 0 is the rational number 0. So that x equals y plus x minus y in alpha plus 0, which implies alpha is a subset of alpha plus 0. And then if x is in the other, the right-hand side, alpha plus 0, then x is equal to y plus 0 for some y in alpha and z in 0. So y plus z is less than y, which implies that x is less than y, which implies that x is in alpha, which implies that alpha plus 0 is a subset of alpha, and because the two sets contain each other, they're the same set. All right, definition, let alpha be a real number, then negative alpha will define to be the set of all negative alpha in the rationals such that x is not an alpha and x is not the smallest element of the rationals minus alpha. We need that second condition to make sure that it's a cut. So we have to make sure that there's no greatest element in the additive inverse. Okay, just a note. We need the condition that x is not. Oh, all right. I just explained this, but we need the condition that x is not the smallest element of q minus alpha. Since, for example, if alpha equals 1, and we naively define -1 to equal negative x in the rational, such that x is not in the set 1, then q minus 1 has a least element, right? -1 would be the least element. Which means that -1 has a greatest element. -1 would be the greatest element. So that contradicts property number 4 for a real number. So we need that extra part there. Okay, here's a theorem. Let alpha be a real number, then negative alpha is a real number. Here we're talking negative alpha stands for the additive inverse of the real number alpha. And here again, we just have to show the four properties are satisfied. So I'm just we're going to be doing this a lot. Just be prepared. Okay, so let's go through the force properties. Property one, let x be an element of negative alpha, then negative x is not an element of alpha. And for any y in Q, y less than x, that means that negative y is greater than negative x, which implies that negative y is not an alpha. And that means that y is an element of negative alpha, right? Property two, alpha is not the whole set of rational numbers. Therefore, the rationals minus alpha is not empty, which means that negative alpha is not empty. Property three, alpha is not the entire is not the empty set. Therefore, q minus alpha is not q. And then finally, property number four, assume negative alpha has a maximal element x naught. Then for any x in the set negative alpha, x naught is greater than or equal to x. Then negative x naught is less than or equal to negative x for all negative x in alpha. This contradicts that for any y in the rationals where y is less than negative x naught, y is in alpha. Therefore, at negative alpha has no maximal element. So every real number has an additive inverse, and the additive inverse is itself a real number. It's a Dedekind cut. Okay, another note here. To prove that alpha plus negative alpha is zero requires the Archimedean property of the rationals, which, as you recall, does not follow from P1 through P12. We talked about that in chapter 28. So we need the Archimedean property to prove this next lemma, and we're going to use this lemma to prove the theorem that comes after it. Right, so the lemma says this: let alpha be a real number and z a positive rational number. Then there are rational numbers x in alpha and y not in alpha, such that y minus x equals z. Moreover, we may assume that y is not the smallest element of q minus alpha. All right, so there's a few parts to this. Let z be a rational number that's positive, then either z is an alpha or z is not an alpha. So case number one, we'll assume z is an alpha. Then assume n times z is also an alpha for all natural numbers n. Then alpha is not bounded, which contradicts that alpha is a real number. Therefore, therefore there is a natural number n in n, such that nz is an alpha, but n plus 1z is not an alpha. Then n plus 1 times z minus nz is equal to z. So that works. Then case two, z is not an alpha. Assume there's no natural number n such that negative nz is an alpha. Then alpha would be empty, which contradicts that alpha is a real number. So there's some n in the natural numbers such that 1 minus n times z is not an alpha, but negative n times z is an alpha. Then 1 minus n times z minus n times z is z. So again, that works out. Lastly, if y is the minimum of q minus alpha, then for z equals y minus x, where x is in alpha, there's some x prime in alpha with x less than x prime, which implies that x prime minus x is greater than 0. And then we can instead take y prime equal to y plus x prime minus x. Then y prime is not in alpha since y is less than y prime. And, we're assuming here that y was the least element of q minus alpha, right? And y prime minus x prime is equal to y plus x prime minus x prime, which is the same thing as y minus x, which is z, and it works out in that case. Okay, now we're going to use that to prove the next theorem, which is that if alpha is a real number, then alpha plus negative alpha is equal to 0. All right, here's the proof. Let alpha be a real number, then alpha plus negative alpha is a subset of 0. Here's the proof. Let x be an element of alpha, y in negative alpha, then negative y is not an element of alpha, implies x less than negative y, which implies that x plus y is less than 0, which means x plus y is in 0. All right, so that shows the containment going from left to right. Right, then we have to show the containment going the other way. Let negative z be an element of 0, then z is a positive rational number. Therefore, there is x in alpha, y not in alpha, and y not the minimum of q minus alpha, such that z equals y minus x. Again, we proved that in the lemma. Then negative z less than 0, and negative z is equal to x plus negative y. Furthermore, x is in alpha, and negative y is in negative alpha, so negative z is in alpha plus minus alpha, and that shows that the containment goes the other way as well, so the two sets are equal to each other. All right, here we have a definition. let P be the set of all real numbers where alpha is greater than 0. So this would be the set of positive real numbers, if you like. Then let's see, we have a note here. Notice that alpha plus beta is in the set P if alpha and beta are in P. Okay, so now we're going to show trichotomy. So if alpha is a real number, then one and only one of the following conditions holds. Right, so either alpha is 0, alpha is in P, or negative alpha is in P. So that's, if you remember, that's called trichotomy. Okay, so here's my proof. Let alpha be a real number. If x is in the rationals, x greater than 0, x is in alpha, then 0 less than x implies 0 is in alpha, implies alpha is not 0. Also, since 0 is in alpha, any y in the rationals with y less than 0 implies y is in alpha, which implies that 0 is a subset of alpha, which implies 0 is less than alpha by the way we defined less than, which implies alpha is in P. If alpha contains no positive rationals, then either alpha contains all negative rationals, in which case 0 is an element of alpha, since otherwise alpha would have a largest element, which implies alpha equals 0. If there's some rational x less than 0 with x not an element of alpha, then negative x is an element of negative alpha, and x is less than 0 implies negative x is greater than 0. Therefore, negative alpha is in the set of positive real numbers. Next, if alpha equals 0 and alpha is in P, then alpha is a subset of 0, which implies 0 contains some positive rational. This is a contradiction. If alpha equals 0 and negative alpha is in the set of positive rationals, then a similar contradiction occurs. Lastly, if alpha is in P and negative alpha is in P, then 0 equals alpha plus negative alpha, which would be greater than 0, which is also a contradiction. So not only, so what we've shown is for every real number, either 1, 2, or 3 is true, and only one of them can be true at the same time. All right, so therefore, exactly one of 1, 2, or 3 is true for any alpha in R. Okay, another note. We need to show that our definition for alpha greater than beta is equivalent with the definition that alpha greater than beta if and only if alpha minus beta is greater than 0, involving the set key that we defined up above. This is a consequence of the following theorem. Right? If alpha, beta, gamma are real numbers and alpha greater than beta, then alpha plus gamma is greater than beta plus gamma. Right? And here's my proof. Let alpha greater than beta, then beta is a proper subset of alpha, which implies there's some x in the rationals such that x is a rational and x is not in, x is in alpha and x is not in beta, which implies for any y in beta, y less than x. Then for any z in gamma, y plus z is less than x plus z, which implies for any y in beta, x in alpha, z in gamma, y plus z is less than x plus z, which implies y plus z is in alpha plus gamma for every y plus z in beta plus gamma, which implies that beta plus gamma is a subset of alpha plus gamma, which implies, by the way, we defined less than or equal, beta plus gamma less than or equal to alpha plus gamma. Furthermore, if alpha plus gamma equals beta plus gamma, then alpha is alpha plus gamma plus negative gamma, which is equal to alpha. Here I'm associating alpha plus gamma plus negative gamma equals beta plus gamma plus negative gamma equals beta plus gamma plus negative gamma, which is equal to beta, which contradicts that alpha is greater than beta. So therefore, that means that the inequality is strict. So alpha plus gamma is strictly greater than beta plus gamma. Okay, got another definition here. If alpha beta are real numbers and alpha beta greater than 0, then we define the product of alpha and beta to be the set that we have written here, the set of all z, such that z is less than or equal to 0, where z is x times y for some x in alpha, y in beta with xy greater than 0. Right? Then we have a bunch of theorems about multiplication. If alpha beta are real numbers with alpha beta greater than 0, then alpha times beta is a real number. Right, so here's the proof. Again, we have to show, the properties. If P is an element of alpha plus beta, if P is an element of alpha times beta and P is positive, then there is xy greater than 0, such that x is an alpha, Y is in beta, and P is XY. Let Q be irrational with Q less than P. If Q is less than equals 0, then Q is an element of alpha plus beta by definition. So assume that Q is greater than 0 and less than P. Then 0 is less than Q over X, which is less than Y, implies Q over X is in beta. So X times Q over X equals Q is an element of alpha times beta. Okay, if P is less than or equal to 0, um, then any Y less than, sorry, lost my place here. If P is less than or equal to 0, then any Y less than P has the property Y is an element of alpha beta. Clearly, alpha not empty, beta not empty implies alpha beta not empty, and alpha not Q, beta not Q implies there are P, Q, and Q such that P is not in alpha, Q is not in beta, and X less than P, Y less than Q for all X in alpha, Y in beta. Then for any X greater than 0, X in alpha, Y greater than 0, Y in beta, XY is less than PQ, which implies that alpha times beta is not all of Q. And then finally, if P is an element of alpha beta and P is less than or equal to 0, then there's some X in alpha, Y in beta with X greater than 0, Y greater than 0, which implies that XY is an element of alpha beta and P is less than XY. If 0 less than P, then P equals XY for some positive X in alpha and some positive Y in beta. Then alpha beta is alpha beta in the is sorry, I'm getting tongue-tied here. Alpha beta real numbers implies there are rationals x prime y prime such that x prime in alpha, y prime in beta, where x less than x prime, y less than y prime. Then x prime y prime is an element of alpha beta, and 0 less than xy less than x prime y prime. Therefore, 0 less than p less than x prime y prime implies alpha beta has no greatest element. So the product of two real numbers is a real number, provided that alpha and beta are positive. So we're only defining this for positive real numbers, right? For now. Right. Another note, notice that alpha beta are in P if the P being the set of positive real numbers. If alpha beta in P, this completes the verification of all properties of the set of positive numbers, positive real numbers. Right. Then we're defining next the absolute value of a real number. So if alpha, excuse me, if alpha is a real number, then absolute value of alpha is alpha if alpha is greater than or equal to 0, and it's negative alpha if alpha is less than or equal to 0. Negative alpha, remember, is the additive inverse of alpha. Right. Another important definition that we'll use to prove some properties of products of numbers, real numbers that are not always positive down below in a few minutes. So if alpha and beta are real numbers, then alpha times beta we define to be 0. If alpha or beta are 0, it's the absolute value of alpha times the absolute value of beta. If alpha greater than 0, beta greater than 0, or alpha less than 0, beta less than 0. And it's the negative of absolute value alpha, absolute value beta, if alpha greater than 0, beta less than 0, or alpha less than 0, beta greater than 0. All right, so like I said, we'll use this to help us prove some of these theorems for when at least one of the real numbers is negative. So here's a theorem. If alpha beta are real numbers, then alpha beta equals beta alpha. So in other words, multiplication is commutative. All right, here's my proof. Okay, property number 1, if alpha greater than 0, beta greater than 0, then for any z in alpha beta, there is x in alpha, y in beta, such that z equals xy, which is the same thing as yx. That follows because x and y are rationals, and rational products of rational numbers commute, if you remember. That implies that Z is in beta alpha, so alpha beta is a subset of B alpha. A similar argument shows that beta alpha is a subset of alpha beta. Therefore, alpha beta equals beta alpha. That's in the case where alpha and beta are both positive. Then for case 2, 3, and 4, where some of them can be negative, follows from the definitions that we had up above. So if alpha beta are both negative, then alpha times beta is the absolute value alpha times the absolute value of beta, and that's a product of positive real numbers, and we know that that commutes, right? And then property number 3, if alpha less than 0, beta greater than 0, then alpha times beta is the negative of the absolute value alpha times the absolute value of beta, and we have a negative of a product of positive real numbers that commutes. We already showed that in part 1. And so that's equal to negative absolute value beta times absolute value alpha, but that's the same thing as beta times alpha. Right, and a similar argument shows it shows that the product commutes for alpha greater than zero and beta less than zero. Um, then case number four, if alpha equals zero, then alpha beta equals zero equals beta alpha by symmetry and the definitions that we had above. So that shows that multiplication is commutative. Multiplication of real numbers is commutative. All right. Next theorem, we show that multiplication of real numbers is associative. And again, we start with the positive case, and then we use the definition that we had up above to show the other cases. So case one, alpha, beta, gamma, positive. Then for any element P in the set, alpha, beta times alpha, beta, in parentheses times gamma. P is of the form x times y in parentheses times z for some x and alpha, y and beta, z and gamma. Then P equals x, y. So you multiply x and y first and multiply by z. That's the same rational number as x times y times z, where you do y times z first and then multiply by x. That follows by associativity of multiplication in the rationals. And that implies that P is an element of alpha times beta times gamma in parentheses. Therefore, alpha times beta times gamma is a subset of alpha times beta times gamma. And a similar argument shows the other inclusion. I just didn't write it out because it's very similar. All right, so we know that associativity holds for products of positive real numbers. Then we have to deal with the other cases. So by the above theorem, we can assume without loss of generality that alpha less than zero, beta gamma greater than zero. Then I'm just using that definition that we had up above. Alpha times beta times gamma is negative times absolute x times absolute beta gamma, which is equal to the negative of absolute value a times, in parentheses, absolute beta times absolute gamma, which is equal to, I can reassociate because these are positive numbers in parentheses, negative in parentheses absolute alpha times absolute beta times absolute gamma. And if you notice from the definition up above, that's the same thing as alpha times beta first times gamma. And the other cases are shown in a similar way, so I just didn't show them. It's done using that definition. All right, another important definition. We define the real number one to be the set of all x in Q, where x is strictly less than one. I'm sorry to keep sniffling, but for some reason my nose is very itchy today. Maybe I'm coming down with something. Here's a note from this definition. It's easy to show that one is a real number, but I skipped it just because we've seen the argument already a million times. You could do it yourself. Just show property 1, 2, 3, 4 holds. Okay, here's the theorem. If alpha is a real number, then alpha times 1 is alpha. All right, here's the proof. If alpha is positive, then for any z less than or equal to 0, z is in alpha and z is in alpha times 1. That just follows from the definition. If z is greater than 0, then if z is an element of alpha times 1, there are x greater than 0, y greater than 0, x in alpha, and y in 1, such that z is x times y, which is less than x times 1, which is equal to x. So that shows that z is in alpha. So alpha times 1 is a subset of alpha. Right? Let z be an element of alpha. There's x in alpha such that 0 less than z less than x, which implies that 0 is less than z over x is less than 1. So that means that z equals x times z over x, which is less than x times 1, which implies that z is in alpha times 1. So alpha is a subset of alpha times 1. So that shows that the two sets are equal to each other. And if alpha is negative, or in other words, if alpha is less than 0, then alpha times 1 is equal to negative of absolute alpha times absolute 1, which is the same thing as negative absolute alpha, which is the same thing as alpha. And if alpha is 0, then alpha times 1 is 0 times 1, which is 0. And that proves the theorem. Okay, another definition. I think we're getting close to the end here. And like I said, this is kind of a long construction. If alpha is a real number, alpha greater than 0, then we find the multiplicative inverse of alpha to be the set of all rational numbers x, such that x is less than or equal to 0, or x is positive, and 1 over x is not in alpha, but 1 over x is not the smallest element of q minus alpha. Again, we need that just so that the multiplicative inverse is a cut. right? If alpha less than zero, then we define alpha, the inverse, the multiplicative inverse of alpha to be the negative of the absolute value of sorry, the negative of the inverse. Sorry, my tongue is not working today. The multiplicative inverse of alpha is the negative of the multiplicative inverse of the absolute value of alpha. Okay. So here's the theorem. If alpha is a real number unequal to zero, then the multiplicative inverse of alpha is a real number. So again, we just have to show the four properties. All right, let alpha be a real number, alpha greater than zero. If x is less than or equal to zero, then x is an alpha inverse by definition. So choose x in alpha inverse that's positive. Then any rational number y, where zero less than y less than x, has the property that 1 over y greater than 1 over x, which is greater than zero. And 1 over x not an alpha implies 1 over y is not an alpha. Also, 1 over x is not the smallest element of q minus alpha, which implies 1 over y greater than 1 over x is not the smallest element of q minus alpha. Therefore, 1 over y is an element of the inverse of alpha. Right, property two, alpha not empty implies that the inverse of alpha is not empty. And then property three, if alpha inverse is a subset of alpha, then alpha inverse is not all of Q. If alpha is a proper subset of alpha inverse and alpha inverse is Q, then for all x greater than zero, x is in Q, and 1 over x is not an alpha. This contradicts that alpha is positive, so therefore alpha inverse is not all of Q. If x is This is property four now. If x is a rational number, x less than or equal to zero, then there is y in alpha inverse with x less than or equal to zero less than y. So assume that x is in alpha inverse where x is positive, then 1 over x not in alpha. Also, 1 over x is not the minimum of q minus alpha. So there is y in q with 0 less than min q minus alpha less than y less than 1 over x, which implies that y is not an alpha, which implies 1 over y is an alpha inverse, and x less than 1 over y implies alpha inverse has no maximal element. Okay, next we need a similar lemma to the lemma that we proved up above for addition, but now we need a similar lemma for multiplication. And I'll explain what this red star means next to the proof in a second. Let me read the lemma out first. All right, let alpha be a real number with alpha greater than zero and z in the rationals with z greater than one. Then there are rational numbers x and alpha, y not an alpha, such that y over x equals z. Moreover, we can assume that y is not the least element of q minus alpha. So you can see it's analogous to the lemma that we had for addition. Uh, the lemma didn't talk about addition, but you know what I mean. A similar lemma that we'll use for multiplication here. Okay, so here's the proof. I wrote a star next to this because the proof of this actually requires a bit of a trick. And I kind of got stuck on this. So I had to actually look at Spivak's proof for this part here. So just so you're aware, to get started on this, you kind of have to use this trick. So this is the trick here is called Bernoulli's inequality, which we've talked about before, but it just didn't occur to me to use Bernoulli's identity on this. So here we can say that, well, let me start here with the assumption. Assume z is an alpha, then z greater than 1 implies z minus 1 greater than 0. And so z to the nth power is equal to 1 plus z minus 1, right? Because 1 minus 1 is 0, so you're not changing the value, all raised to the n power, which is greater than or equal to 1 plus n times z minus 1 by Bernoulli's inequality, right? That implies that z to the n cannot all be in alpha for all n in n. Therefore, this is therefore there is a k in n, the natural numbers, such that z to the k is an alpha and z to the k plus 1 is not in alpha. And if we choose x to be z to the k and y to be z to the k plus 1, then y over x obviously is equal to z. All right, number two, if y is z to the k plus 1, which is equal to the minimum of q minus alpha, then we can take x prime in alpha, where x is less than x prime, and substitute y prime equals y x prime over x, which is the same thing as z to the k plus 1. times x prime over x, then y is less than y prime, and y prime over x prime is equal to z. Right, so that takes care of that case. And then finally, case number 3 assumes z is an alpha. Since z is greater than 1 over z is less than 1, and 1 over z to the n, that implies that 1 over z to the n is less than 1 for all natural numbers n. If 1 over z to the n is not an alpha for all n, that implies that x is uh, a rational number, x greater than 0, such that 0 less than x less than 1 over z to the n for all n, which implies 1 less than z to the n less than x for all natural numbers n, which contradicts that 1 plus n times z minus 1 is less than x for all n in n. Therefore, there's some k in n where 1 over z to the n is not an alpha, but 1 over z to the k plus 1 is an alpha. Then if we choose x to be 1 over z to the k plus 1 and y to be 1 over z to the k, then y over x is equal to z, and that proves the lemma. Okay, and then we're going to use that theorem to prove we're going to use that lemma to prove some theorems about multiplication in real numbers. So if alpha is a real number and alpha not 0, then alpha times alpha inverse is equal to 1. Or no, in other words, uh, alpha to the minus 1 is the multiplicative inverse of alpha, provided that alpha is not 0. Okay, so let alpha be a real number that's positive for any x in the rationals, x less than or equal to 0, x in alpha times alpha inverse if and only if x is in 1. So we can assume that x is in alpha, y is in alpha inverse, xy positive. Then 1 over y is not in alpha, implies x is less than 1 over y, which implies x times y is less than 1, which implies that xy is in the real number 1, right in the cut. Then alpha times alpha inverse is a subset of 1. So that shows containment going one way. Next, let z be in 1 and z be a positive number, a positive rational number. Then 1 over z is greater than 1, which implies there is x in alpha, y not in alpha, such that y over x equals 1 over z, which is greater than 1. And y over z is not the minimum of the rationals minus alpha. Then y is not in alpha, implies 1 over y is in alpha inverse. And z equals x over y is the same thing as x times 1 over y. And x times 1 over y is an element of alpha times alpha inverse, which implies that 1 is a subset of alpha times alpha inverse. So that shows that it's true for positive real numbers. Then we also have to deal with other cases. If alpha is less than 0, then alpha times alpha inverse is equal to the absolute value alpha times the absolute value of alpha inverse. So, no matter what, when you multiply non-zero real number, when you multiply a non-zero real number by its inverse, you get the real number 1. Okay, next we'll show multiplication of real numbers is this is the distributive law rather. So if alpha, beta, and gamma are real numbers, then multiplication distributes over addition. And I think this is the last proof? Yeah, this is the last bit. This is kind of a long argument though. Okay, so let's do this for positive real numbers first, and then we'll handle the other cases using the definition that we had up above a few minutes ago. All right, so case 1, assume alpha, beta, gamma positive, then any x less than or equal to 0, x in alpha times beta plus gamma, if and only if x is an element of alpha, beta plus alpha, gamma. So assume that p is an element of alpha times beta plus gamma, where p is positive, right? It's because the negative ones are in both of the sets by definition. Then there are x in alpha, y in beta, z in gamma, xyz positive, such that p is equal to x times y plus z in parentheses. Then p is xy plus xz by the distributive law on Q. So p is an element of alpha beta plus alpha gamma, which implies that containment goes from left to right. And we have to show the containment goes the other way as well. Next, let p in alpha times beta plus alpha times gamma. Then there are x prime in alpha, y in beta, z in gamma, with x prime, y0 positive, and p equals xy plus x prime z. Here we can't assume that the two elements of alpha are the same alpha, right? So that's why we have x and x prime. If x less than or equal to x prime, then p equals x prime. So here I'm sort of factoring out, not sort of, I'm factoring out the x prime. So p is then equal to x prime times x over x prime times y plus z, which is less than or equal to x prime times y plus z, because x over x prime is less than 1, right? Which implies P is in alpha times in parentheses beta plus gamma. And a similar argument holds if x prime is less than or equal to x. Therefore, alpha beta plus alpha gamma is contained in alpha times beta plus gamma. So that shows, at least in the case where all three of the numbers are positive, that the distributive law holds. And then we have to take care of the other cases. So actually, there's only really one other case that takes a lot of work, but it's if alpha positive, beta less than zero, gamma greater than zero. If beta plus gamma is if beta plus gamma is non-negative, then alpha times gamma is equal to alpha times beta plus gamma plus the absolute value of beta, which is equal to alpha times beta plus gamma plus alpha times absolute beta. And if you add, what am I adding to both sides? I'm adding alpha beta to both sides of that. We get alpha beta plus alpha gamma equals negative of alpha times absolute beta plus alpha times beta plus gamma plus alpha times absolute beta. And the negatives cancel each other, and we get alpha times beta plus gamma. And the other case, if beta plus gamma is negative, is non-positive, then alpha times absolute beta is equal to alpha times absolute beta minus gamma plus gamma, right? It's like adding zero, uh, equals alpha times, in parentheses, negative absolute beta plus gamma, which is equal to alpha times absolute beta plus gamma plus and then plus gamma without the absolute value equals alpha times absolute beta plus gamma plus alpha gamma. Then zero is equal to alpha times absolute beta plus negative alpha times absolute beta equals alpha times absolute beta plus gamma plus alpha gamma plus negative alpha times absolute beta implies negative of alpha times absolute value of beta plus gamma equals negative alpha times absolute beta plus alpha gamma, which is the same thing as alpha times in parentheses beta plus gamma is equal to alpha beta plus alpha gamma. All right, so that shows in at least in those two cases, the distributive law holds, and all the other cases actually follow from symmetry in the definition for multiplication, and the commutative law for addition and multiplication, and part one and two above. So I didn't bother writing them out; they follow from those things. So I didn't write out the details because I didn't feel like doing it. Okay, so that shows all of the properties that we need for the real numbers. So we showed that the real numbers with our definitions is a field. Not only that, it's an ordered field because we showed that um, there's a total order defined on the real numbers, and we showed that the field is complete, right? Every set of real numbers that's bounded above has a least upper bound. Okay, so this completes the proof that there exists a complete ordered field. In chapter 30, which is the last chapter in the epilogue for Spivak, we'll show there's only one complete ordered field. Therefore, P1 through P13 are sufficient to completely characterize the real numbers, and anything about R can be proven on the basis of properties P1 through P13. Okay, so that's a long one. Now we're done with the construction of the real numbers. Now we just have to show that the construction is unique. Let me stop my screen share for a second. So I want to say something real quick at the end about the exercise set for chapter 29. There's only two questions in the exercise set for question 29, and I'm not going to do them. The reason for that is we've actually already done the first question in tau. So if you remember, we constructed the real numbers in tau using Cauchy sequences. Question one in the exercise for chapter 29 says construct the real numbers using Cauchy sequences. So we've already done that. There's no point in doing it again. And then question number two is about constructing the real numbers using the decimal representation for real numbers, but we're going to do that in tau eventually. So I'm not going to bother doing it here because we'll do that in tau's appendix B when we get around to it eventually. Um, so I'm not going to make a video on the exercise set for chapter 29 because there's no point. So we'll go on. The next video that I'll post in Spivak will be the summary for chapter 29, and there is an exercise set for chapter 30, and there is an exercise set for chapter 30 where we'll do some or all of the questions. I haven't looked at them, but Okay, so that was a long one. Thanks. If you stuck to the end of this video, thank you for doing that. I do want to say one last thing before I end this one. Um, I talked about the fact that I restarted my Patreon page. And if you want to join the Patreon page, you have access to the PDF files for all of my summaries and exercise solutions for all my videos. For example, here, these are all the ones that I've done so far in Spivak's book. I have all the ones here for Tao's book, Analysis One, at least, the ones that I've done already, and for all the other math videos that I've done on the channel as well. So for $3 a month, you can get access to that stuff. I always, I'm going forward. I'm always going to be posting the PDFs for the stuff that I go on about on the channel here to the Patreon page. So if you want to download the files, you can do that, but you have to join the Patreon, which, like I said, is $3 a month. And when I find mistakes on previous uh, PDFs or in previous videos, or if someone notices a mistake, I always update the corrections here on Patreon. So just something I wanted to end on here. So again, thanks for watching through this whole video. I'll I'll be merciful and let you guys go now. And I'll see you in the video for chapter 30. All right, keep learning, everybody.